¿Estamos listos para iniciar?
Sí, sí, totalmente.
We're about to start, doctor.
Okay.
Hola, buenas tardes. Buenas tardes, Panamá.
A todos los participantes, a los profesores. En nombre de la Dirección de Investigación de la UIPE, le agradecemos su participación esta tarde a todos en nuestro tercer ciclo de conferencia I+D. Le recordamos a todos que esta conferencia va a estar dictada en inglés. Para dar inicio, lo dejamos con el director de la Dirección de Investigación, el profesor Carlos Medina, para dar las palabras de bienvenida. Muchas gracias a todos por su asistencia.
Welcome, everyone. It's a pleasure to have you here all. I'm pretty sure it will be a great evening with a lot of information. So we are grateful to Dr. Yoshihiro Ishitani from University of Chiba, Japan, for his participation in this conference. We also are very grateful to Dr. Ritter Diaz for accompanying us. He's a representative director of Japan Association for Promotion of Latin America and the Caribbean. And he will also give us some words and his contribution to an important relationship between Panama and Japan. Dr. Ishitani have gave us his time and to bring us two really interesting topics. One is related directly with his research, scientific research, and the other is related to also his experience around or related to higher education. So both topics are really, really important for us, and I hope everyone will enjoy it this time. Thank you very much. Dr. Ritter, I think, well, you can give us some words.
Okay, thank you, Dr. Medina. Good evening, everyone. I'm Ritter Diaz, Director Representative of the Japan Association for Promotion of Latin America and the Caribbean, JAPOLAC, and I am a former ambassador of Panama to Japan. First and foremost, I would like to express my sincere gratitude to Dr. Zoila Castillo for organizing this lecture and for her tireless efforts to advance academic innovation at the Panama Technological University, UTP. I would also like to extend my thanks to Dr. Yoshihiro Ishitani from the Graduate School of Electrical and Electronic Engineering of Chiba University for accepting UTP's invitation to deliver today's lecture on semiconductors, sharing his line of research and experience in implementing the semiconductor program in Myanmar University under the technical assistance of the Japan International Cooperation Agency. JAPOLAC is dedicated to promoting international education between Japanese and Latin American and Caribbean universities. Within JAPOLAC, one of our key focuses is education in artificial intelligence, given the significant changes triggered by the digitalization of human activities and more recently, the emergence of large language models such as ChatGPT, which have generated considerable anxiety worldwide. In this regard, JAPOLAC is supporting UTP in establishing academic and research partnerships with Japan in the field of semiconductors and recommend that UTP reach out to the Faculty of Engineering of Chiba University to explore possibilities for academic exchanges in the field of semiconductors, resulting in this online lecture today. Now allow me to briefly touch upon the academic cooperation between UTP and Chiba University, which began in 2015 with the first international conference on controlled environment agriculture, jointly organized by Chiba University, UTP, Panama University, SENACIT, and other institutions. In 2016, Chiba University signed the first academic exchange agreement with UTP and Panama University, enabling 25 Panamanian students to travel to Japan and learn about controlled environment agriculture, and 20 Japanese students to travel to Panama to study endemic orchids, coffee, and other agricultural products. In 2017, again, in partnership with Chiba University, UTP, Panama University, SENACIT, and other institutions hosted the second conference on controlled environment agriculture. Thanks to this academic cooperation with Chiba University, UTP established the first laboratory of controlled environment agriculture last year, providing training for students and researchers in this cutting-edge technology. Additionally, the Panamanian government established the Research Center for Agricultural Production in Controlled Environment, CPAC in Spanish, to disseminate this technology in Panama and the Latin American region. I believe that the knowledge transfer in controlled environment agriculture will equip Panama to better cope with the challenges posed by climate change to traditional open agriculture, ensuring food security even in adverse climatic conditions. Furthermore, in 2021, and in the middle of the pandemic, UTP and Chiba University launched the first online program to educate Japanese students about Panamanian culture, the Panama Canal, logistics, and Central American tropics. Thus far, both universities have successfully conducted 4 online programs, and the next one is scheduled for September this year. Today, we embark on another area of academic cooperation with UTP and Chiba University, focusing on semiconductors. The semiconductor industry has become a focal point of technological competition between the United States and China. This is because semiconductors play a critical role in the fabrication of chips, which are essential components in virtually all electronic devices and machines, ranging from computers and smartphones to advanced missile systems and fighter jets. As you may be aware, advanced semiconductors are crucial for the development of artificial intelligence, making it a matter of national security for many countries. Japan also holds an important position in the global semiconductor industry, particularly in semiconducting materials and chip-making equipment manufacturing. I hope today's lecture will contribute to the formulation of new academic programs and create an enabling environment for training of students, professors, and researchers in the intricacies of semiconductors. Thank you very much.
Muchas gracias, doctor Ritter. Como todos saben, para nosotros es muy grato tener un conferencista como el doctor Yoshihiro Ishitani, de la Escuela de Graduados de Ingeniería Eléctrica y Electrónica en Chiba, Japón. Ha llevado a cabo investigaciones en Hitachi, donde se construyeron diodos láser emisores de luz roja en producción masiva. Actualmente, su investigación se centra en nitruros Tercer, como el galio nitrógeno, especialmente en la emisión de luz ultravioleta y en otros materiales 3-UV, abordando el problema térmico y la tecnología cuántica relacionada. Además, es miembro de varias asociaciones, incluyendo la Sociedad Japonesa de Física Aplicada y la Sociedad de Semiconductores de Banda Ancha de Japón. El doctor Ishitani nos estará presentando 2 temas: investigación fundamental sobre semiconductores del futuro y el proyecto JICA para mejorar la educación en ingeniería en Myanmar. Thank you, Dr. Ishitani. Y nuevamente a todos los presentes, quienes han tomado de su tiempo para acompañarnos, esperamos que la información brindada el día de hoy sea provecho para todos. You can start, Dr. Ishitani.
Okay. Okay. Thank you for kind information and introduction. Okay. So could you see my file? PowerPoint file. Could you see? Can you see?
Yes, we will. Yes, we will, doctor.
Okay. Okay, I'll start. So my name is Yoshihiro Ishitani of Chiba University, Japan. So this is my title, and today I thank you very much for inviting me. So this meeting, And I will talk about the fundamental research direction. So, so what class, so industry and the development research. And I will introduce my research topics. And next, I will also have some talk about my experience on joining the JICA project for support of Myanmar University, so Yangon Technological University and Mandalay Technological University. These two universities are top two technological universities in Myanmar. Okay. So this is outline. At first, I will introduce the various semiconductor devices, and particularly in Japan, the material analysis and the material research is very advanced. So I will talk about this point. And so as examples of electronic devices, photonic devices are introduced. So particularly for photonic devices, UV, visible, and IR regions. And so on the basis of this status quo of world research points, and I will talk about the research fields at present. So many people are now focusing. And next, I will introduce my research viewpoint and how to conduct systematic research on semiconductors. This is very important. Yeah. And next, enhancement of engineering education in Myanmar. So this is was the JICA project. And summarize my talk. So at first, this is a brief history of semiconductor technologies. So from 19th century, some experimental results and experimental facts have been found. But in 19th century, the fundamental physics is uncovered. So, and in middle of 20th century, so many physical properties were clarified. And in the middle of this century, so bipolar transistors and semiconductor lasers. So this very important device prototype were developed. So this is these are the base of the present semiconductor technologies for computing and communication. Okay. So at present, so semiconductors are applied to various fields. So, for example, energy harvesting by solar cells, but thermoelectronic elements will be very important for energy harvesting from the heat energy to converting the heat energy to electric energy. And now the development of logic devices and power devices are very important. And of course, now silicon is widely used, but for high power devices, silicon carbide is important. And further, gallium nitride and other new materials are now under developing. For the communication, of course, 1.55 micrometer lasers have been used, and so you are now using. So, but for future communication, quantum communication is very important, and single photon emitter is one of the options. And for display, we can utilize the very beautiful display. So using organic LEDs, and but for AR and VR, so organic materials is not so good because of the heat problem. Conventional phosphide semiconductor is also not good because of that heat problem. So nitrile semiconductors is a very important candidate to fabricate the very very clear AR and VR image. And now because of the COVID-19, this pandemic was a very, very severe problem. And people are now focusing on the hygiene and sterilization devices. So by using natural semiconductors, it is possible to fabricate 260 nanometer wavelength. So, but there is a very high barrier to develop these LEDs. And first, I will talk about the LSI and the ULSI, this logic devices. So conventionally, silicon is widely used, but for gallium arsenide, so the electron mobility is higher than silicon. So the high rate information process is possible. This device production, so there are several steps: pre-process, dicing, bonding, and sealing. And in pre-process, this is very important step, and this must be in a clean room. And water must be purified, and air must be, of course, purified. And sodium in water is very toxic for the device fabrication. So bacteria and very tiny dust must be also excluded. So this is very important. So how to clean the surface of the wafer? So this is a very important and very severe problem. And the material of silicon gallium arsenide, these are very advanced crystals, and silicon is has a very high purity, more than 11.9. And the gallium arsenide crystal quality is far lower than silicon, but so it is far better than gallium nitride and silicon carbide. So dislocation density is 10 to the second. And gallium nitride at present a middle of 10 to the 6th. So, but on this wafer, so epitaxial layers are grown. In this case, the dislocation density less than 10 to the 4th is reported. And in the conventional lasers, so this level is indispensable, but for gallium nitride, this is enough. So this is the clear difference of the feasibility for lower crystal quality. So in the case of gallium nitride, even though the crystal quality is worse, far worse than that of gallium nitride, but the fabrication of laser is possible. But in the case of logic devices, HEMT, if it is in this case, dislocation reduction is very important. And now for power devices, silicon carbide is developed, and power device has been practically used in the Super Express train in Japan in 2020. And now the heated topic in the world is nano device technology. So advantage is for the integration is production cost and high frequency and operation power. And about 10 years ago, the size of the circuit is 40 nanometer and reduced to 20 nanometer. So, but now, companies in world is competing toward the size of 3 nanometer and 2 nanometer. And for the reduction of this size, planar, so conventional planar FET is not so good. So, and fin type, this type gate structure and channel structure has been developed. So, but it was firstly proposed by Hitachi Company in 1989. So, but at this stage, the mass production was impossible. And about 20 years later, Intel has firstly successed in manufacturing. So it took about 20 years to fabricate this structure. So this is a very high level of fabrication and device process. But this is not enough for 3 and 2 nanometer size, and gate-all-around structure is required. And Samsung Electronics has already started the research, and TSMC of Taiwan will scheduled to fabricate this type structure, and Intel has also started. And IBM and Rapidus in Japan, they are contracted for the collaboration, research, and mass production. And that project has started in 2022. So this is a status quo of the research and development for 3 nanometer, 2 nanometer device structure. And this is the rough image of power devices and HEMT devices and the relation of the power and switching frequency. And now silicon is widely used, and the silicon carbide is practically has been applied to practical usage. And in the super express train, this is used. So, but for EV and other switching devices, a higher frequency is required. In this case, silicon carbide is not enough. So this is mapping of material, appropriate material. So silicon is here, and silicon carbide is here. So because this is these are the materials in these materials, the electron mass is heavy than germanium nitride and other direct transition type semiconductors. So germanium nitride is feasible for high frequency and high power. So this is a very desirable material for this application to high power and high frequency devices. So people are now focusing on germanium nitride. So next is photonic devices. This is the view graph for band gap energy and the lattice constant. These are nitride. And these are the conventional 3-5 materials, aluminum, gallium, indium phosphide on gamma arsenide. So this material is widely used for red light emitting devices, but it is impossible to fabricate green light LEDs and lasers. So gamma nitride was developed, and indium nitride. And here, so blue color LEDs and lasers was fabricated. So, but green color had a barrier. So, but now it is possible, and we can use the blue color, green color, and red color devices. And in the color mapping, we can, so because of this development, we can utilize the beautiful display. Okay, but for the monolithic growth for micro LEDs for AR and VR, so gallium indium nitride, so high indium content gallium indium nitride is desired. So, but it is very difficult because of the large lattice mismatching between gallium nitride and indium nitride. That is about 11%. So this is very, very high lattice mismatch. Okay, and for the UV region, there are many application field of the hygiene program and also the information technology and so on. And there are many several lasers based on the gas laser. So this laser size is large, and we can reduce the laser size by using the diode laser. So, but this is the external quantum efficiency of the conversion, energy conversion from electric energy to photonic energy. So this is a case of LED, and below 400 nanometer, the efficiency decreases drastically. And below 350, so the efficiency about 1% or less. So now for the hygiene application, 260 is desired, but in this case, less than 1%. This is a very severe problem. So this is because the high rate of non-radiative electron hole recombination. And people are now focusing on this point, but so actually low radiative recombination rate by heating is hindered. So, but people are now focusing, mainly focusing on this problem. So my viewpoint is control the heat energy is very important to enhance the recombination probability itself. And this is the IR region. Take an example of quantum cascade lasers. This is under development, so everywhere in the world. So, but operating temperature is limited. So this is in the middle of frequency. So the temperature is 200. So some cooling is necessary, but for terahertz region, so low level terahertz region, cooling to liquid nitrogen is required, and for higher frequency region, of course, it is a very high technology is required. But if this is fabricated, we can utilize this wavelength for the communication, high rate communication, high frequency communication between cars, and traffic system will be changed. And so for this application, people are now researching in many fields. At first, reduction of lattice defects. This is very, very important. And most of the work is on this topic. And point defects and the complexes is considered to be the origin of non-radiative carrier combination. And of course, this point defects and also the threatening dislocations are the source of the electron scattering in FETs. So the research is classified to 2 points for the bulk growth and epitaxial layers growth. And bulk growth monothermal HBP and natrium sodium flux and some other methods applied. Being applied, and for epitaxial layers, MOVP and sputtering MB. So mainly MOVP and MB have been conventionally researched, but most of the mass production was conducted by the MOVP. So, but now sputtering is found to be a very good special method of sputtering. It's good for fabricating the high energy gap materials of gallium nitride, aluminum nitride, and so on. And on the basis of this crystal technology, energy diagram control and conductivity control will be conducted. And in this case, superlattice control, even for one monolayer, is now researched. For example, I think there are many milestones for the practical fabrication of graphene and bronze nitride and transition metal, discalcogranite. So, but in contrast, aluminum nitride, one monolayer gallium nitride, aluminum nitride, this kind of structure is based on the crystals we can utilize at present. So these studies are also conducted. So, but a very high level of crystal quality is required. And quantum dots for a single photon emission is also researched. And for wideband gap material, p-type conductivity is very difficult. So not only the atomic doping, utilizing the polarization field in the multi-layer structure. So this is also utilized, and for aluminum gallium nitride materials, so whole concentration required for the device operation is conducted by this method. And but when we consider the future device technology, heat energy problem is very severe. For transistors, Lee current, and electron scattering. So electron scattering increases the resistivity. So, but in this ohmic heating, so produce heat energy. And heat energy produce more ohmic heating. So this vicious cycle takes place in the present devices. And LEDs, lasers, the situation is similar. And non-radiative electron-hole combination produce heating energy. And heating energy enhances this non-radiative carrying combination and also reduce the radiative recombination probability. So this is very severe problem. And solar cells maximum energy conversion efficiency is 47%, but this is research stage, not in the practical use. And in this case, no use for long wavelength region. And for high short wavelength region, so because of the energy relaxation of electrons from the excited level to the band bottom. So because of this energy relaxation, so heating energy takes place. And this heat energy is wasted. So this is a main loss, and because of this, the top value is less than 50%. So if we can utilize the heat energy in solar cells, that energy conversion efficiency will be improved much more. So on the basis of this present status, our research topic is the game changing by utilizing phonon control and the integration of photonic, electronic, and photonic functions. And the application, because of the application to AI and EV, so the heating energy will be increased much more. So drastic increase will be is expected. So by using semiconductor devices. So to handle the heating energy is very important for the high performance of devices and control the so heating. Leakage of the heating energy to the air. So this is a very severe problem. So I think that this development of semiconductor device is meet with the SDGs, some SDGs goal. And these are members of my laboratory, and so 3 staffs and 2, 3, or 5 PhD students, but one of the PhD students cannot come to my laboratory because she's from Myanmar, and because of the social problem in Myanmar, she cannot go outside of Myanmar. And 9 master course students and 4 undergraduate course students. And so, as I said, research field is toward the future society, meeting SDGs and IT and EV technologies. We have to control the heating energy in devices. And in our daily life and the infrastructures and the industries, much heat energy is fabricated. And some of the heating energy can be reused in these instruments. So this is very important. So this is an image of the semiconductor devices. In the active region in devices, heating energy takes place. And if we can extract this heating energy to outside of the devices, and we can reuse this heating energy. So by using the thermoelectronic elements to fabricate, to convert the heat energy to electric energy. And also if we can use the heat energy to produce the electromagnetic waves for communication. So this is very good. And by extracting the heating energy from inside, so this is directly leads to the high performance of this device itself. So this is a dispersion curve of phonon energy. So the abscissa is the momentum of phonons, and ordinate is the phonon energy. So now we usually, so when we usually use the word of heat energy, so this low energy dispersion, these low energy acoustic phonons are considered. So now people are now focusing on this phonons, but in FETs and lasers and LEDs, so most toxic phonon is this longitudinal optical phonons. Optical phonons is most so produces most severe problem. And but even though the percentage existing LO phonon is very small compared to the acoustic phonons, but very small amount of this optical phonon gives the severe effect on device operation. So this is the control of this longitudinal optical phonon is very important. So now wide bandgap materials is under research, and probably these materials will be applied to many devices. Examples aluminum nitride, gallium nitride. And when we consider nitride system and oxide system, so this alternate means the interaction strengths of electrons and phonons. So nitride system has very strong interaction of electron and phonon. And so this wide bandgap material is very important for the future application, but simultaneously it suggests that heating problem is will be very severe. So the control of phonon is very important. So these are our approaches. So to extract phonons from inside to outside. Of course, we are discussing the non-thermal equilibrium phonos. And utilize the phonon energy to produce the electromagnetic wave. And how to control the interaction of extents for the high efficiency UV light emission. So the interaction of extents and phonons. So how to control. So this is a very important topic. And how to utilize the heating energy, so in solar cells. So this is very important to enhance the conversion efficiency. And we are using various instruments. So I will introduce these points. And in my group, to 3 research groups of this one, and but so experimental groups and simulation group. So roughly these 2 groups. This is classified. So, but we don't do the crystal growth because so very very expensive. Instrument, and so many researchers are required. So this crystal growth is conducted by other university and collaboration. So this collaboration is very important to conduct the big project. So these are our instruments, photoluminescence system and double laser microscopic Raman scattering system, and FTIR system, and photolithography system, including the SEM. Okay, what can be observed for the phonon dynamics? This is very important, and because of the diffusion transport and also the ballistic, quasi ballistic region, and because of the phonon is waves, so the diffraction and such effect will be also included. So in the nanoscale structure, so by controlling this, these processes are very important. And what happens in the crystal, we are now researching and how to measure the phonon transport. So this is a very important topic. And in our in my laboratory, so I have introduced this Raman imaging, special Raman imaging system using double lasers lines simultaneously instant on the sample. And for the UV light, the heating energy is fabricated, and by using another lasers, the heating condition in underlayer is observed. And by this measurement, we can discuss the energy transport across the heterointerface. So in the multi-layer structure of devices, the heating phonon transport across the heterostructure is very, very important. So this is an example of the observation. So there are some domains with crystal defects and without crystal defects. This is a photoluminescence mapping. So dark line is the place of the high density of crystal defects. So the light emission intensity is weak. And this is a low crystal defect region. High luminescence intensity is observed. And we introduced the heating lasers and measure by using green light lasers. This is the Raman signal with and without heating lasers. And this is a mapping image of 8 micrometer and 8 micrometer square region. And this granular underlayer is monitored. And this is without heating lasers and with heating lasers. And this view graph indicates the lattice vibration frequency. When lattice vibration frequency is decreased, it indicates that temperature is increased. So when we compare this view graph and this view graph, this view graph indicates the lower lattice vibration frequency, indicating the temperature increase. So, but we cannot see any structure of this triangle or structure. So, but when we take the difference of this image, so here, so at the same point, the difference of this difference is monitored. So in this case, this is a result at the same position. So we can see this triangle structure. So this is a photoluminescence. In the photoluminescence image, we can also observe the same structure. But in this case, this is monitored. So by the upper layer, gamma-indium upper layer, this is monitored for the under layer. So monitoring layer is different between this one and this one. So this structure says that at the defective region, phonon cannot be transported to under layer. So, but high crystal quality region, phonon transport and thermal conductance is high. So the crystal quality is very important for the extraction of thermal energy. And we have successfully monitored this phonon transport across the heating energy. So this is published in Applied Physics Letters, and this is designated for the editor's pick. And we have also we can monitor the lateral phonon transport. So that this shift of the Raman peak wave number means the temperature increase. So the temperature is decreasing. So from the heating position to outside of the heating position, and the lateral energy transport about 10 micrometer order was monitored. Okay, the time is. So I will hurry up. And so next is the IR emission. So now quantum cascade laser is widely used or widely researched. but in this case, a very low efficiency of energy conversion. And probably the efficiency is about a few percent. So, but at high temperature, so it is very difficult to obtain the optical gain. So the cooling is very important. But when we utilize phonon system, no cooling is necessary because heat energy is the energy source of the light. So no problem for heating. Okay. And conventionally, surface phonon protons using nanostructures have been developed, but in this case, there's a big problem that wavelength depends on the emission direction. So this is very severe problem. So, but in our case, not so minor structure, so very easy to fabricate this structure. So this mesa structures fabricated and samples attached on the heater, and the thermal radiation is monitored by the FTIR system. And this is a system, and this is a result. So by using the gamma arsenide, and gold film is deposited some part partially on the surface, and we have observed the yellow phonon resonant emission at 8.5 terahertz. So this is very important because this says that we can convert the heat energy to the electromagnetic energy. So that can be used for the communication. And so right-hand side figure is important. So by changing the emission window, we have minimizing this window region, controlling this window size, and from bulk no window structure, 70 micron, 10 micron, 6 micron, and 1.5 micron. And this very clear emission structure was obtained. And so, so it says that, and also for gamma nitride, the same structure, type of structure was fabricated, and in this case also, we have observed very clear emission and the reduction of the background emission was conducted. And this is a simulation of FDTD. FDTD is the simulation by solving the Maxwell equations. And this is the component of emission. So this two graph is for the polarization difference. So this case, the polarization is perpendicular to this sheet, and this is the polarization vertical. This is a parallel to a perpendicular this sheet and parallel to the stripe direction. And in this case, perpendicular to the stripe direction. So this direction. In this case, only in this case, this emission component is observed. This is also the case of the experiment. Only for the polarization perpendicular to the stripes, this emission is obtained. So this is that photonic system is very important. And now our final topic is the support for the Yangon Technology University and the Mandalay Technological University. But JICA project is for various countries and fields. And for Panama, several JICA project is now undergoing, including the monorail vehicles. And for the Latin America, some education support is conducted. But I think for the university, education and research support is very important. That was conducted for the Myanmar. So this project for Myanmar was implemented for about 6 years. And education system was changed, so we constructed a syllabus and for these topics, and the lecture method is also changed. So at first they are only reading textbook, so but that is not good. So we have trained the teachers of Myanmar universities. And also research supporting, in our case, supporting electronics and electronic research. And wideband gap semiconductors, carbon nanotubes, electronic devices, photonic devices, wireless communication using radio waves. So various topics were introduced. So because Okayama University, Niigata University, and Kansas University, Nagasaki University, so from several universities, professors joined this project. And the research building was so we fabricated, and a series of experimental instruments have been provided. So this is a research building built by a JICA project. And for semiconductors, visible UV spectrometers and microscopic FTIR and metal deposition system, photolithography system, SEM, these instruments have been introduced. And also the training of operation training was also conducted. But because of the COVID-19 and the social issues, this support was quitted in 2020. Teachers are unwilling to exploit this experimental system because they have a little budget. And also, if some instruments are out of order, they cannot repair. So this is a very severe problem. So they are not willing to use the experimental system. And also they are not familiar with the experimental work. So this is also a big problem. So I'm now introducing some students and teachers to our university. So in 2019, we have accepted 17 attendees, but COVID-19 from 2020 to 2022 online plan was conducted. But this year, so we will actually accept for the research base 3 weeks visit, and 5 students will come to my university. So this is photos in 2019. So semiconductor technologies are going to entering a new dimension of world, and so very minute and nano process is really important. So in this case, not only introducing the high level instruments, so but also the accumulation of technologies know-how is very important, because Japan is a top runner of the instruments of production system, but we cannot at present fabricate the structure of 10 nanometer scale logic circuit. So this is very severe problem. So that is because at present accumulation is know-how is lacking in Japan. So education of engineers is very, very important topic. Probably this is also the case of Panama. And in my research, so probably, I think that technologies meeting SDGs will be very powerful source of industry because European countries are going to this direction. So when we consider the case of Panama, so education is very important, and also there's a very many possibilities to develop the education, the semiconductor technologies, and introduce factories and research topics from United States and also from so various countries. So it is my pleasure if I can contribute to the support to Panama's education and research on semiconductors. Thank you for attention. I'm sorry to so very long talk. Thank you.
Thank you so much, Dr. Ishitani. We have several questions, but time is over. So,
I'm sorry.
Okay, Elida, Elida de Valdía is one of our team semiconductor, and he is raising her hand. So go ahead, Elida. Not the microphone is closed, Elida.
Okay, sorry. Excellent talk. Thank you so much. It was very enlightening to see what's going on in 3.5 semiconductors and why band gap. But one of the things that really interests me was that you said that we actually can do 3.5 compounds with sputtering. Can you elaborate a little bit more on that? Because MBE systems and the other systems are kind of beyond what we can achieve in Panama at this time, but sputtering is something that we could probably adopt. So can you elaborate a little bit of how that is possible to do 3.5 compounds or epitaxial layers, I guess, using sputtering? And I'll appreciate your answer and I'll take it off the air. Thank you.
Okay, about the sputtering method. Sputtering method is now under focusing, but in this case, so this is a special sputtering method using plasma excitation of material or laser sputtering. So lasers incident on the material, and high energy atomic source is deposited on the wafer. So usually the sputtering is so plasma is materials are in the plasma, and materials is vapored and deposited on the wafer. And active atomic species very harmful for the so crystal growth. So this is a very severe problem. So, but in this case, the distance of the wafer and the plasma source is very important, and also the pulse supply of the plasma is also important. So the sputtering instruments is highly developed. So it is just similar to the MBE. So I think so it is somewhat sort of MBE. So, but that is sputtering. So, but
Okay.
that is a sort of MBE.
Okay. All right. Thank you so much for your answer.
Thank you.
Thank you so much, Dr. Ishitani. I'm so sorry because there are a lot of questions. I'm going to send to you the questions, and maybe you have time to answer by email, send it to us, and we will send it to the public. Thank you so much again. And the best part I like is collaboration with Panama is very welcome.
Thank you. So yeah, I'm also welcome. So for the Sakura Science Plan next year, so if possible, I'd like to do with Panama teachers and students. For young teachers, they are also can attend the Sakura Science Plan. So it is very welcome for us.
Thank you. Thank you so much. Gracias a todos los participantes. This was a very interesting and excellent presentation. Thank you so much, Dr. Ishitani.
Gracias a ustedes por la invitación.
Thank you.
Excelente.
And also, you know, because of the questions, the people are very eager to know more about semiconductors, phonics, and everything. Okay. Thank you. Gracias a todos los participantes. Y bueno, los esperamos en unas próximas conferencias de la Dirección de Investigación en los ciclos de conferencias. Muchísimas gracias. Oh, a lot of questions, Dr. Ishitani. Wow. People are very, very interested in the topic. I'm going to send the question, Dr. Ishitani, to you.
Yes.
Okay.
Dr. Ishitani, how are you with your time right now?
Yes, I have time today in the morning, so I have enough time. So,
Dr. Zoila, maybe we can take some more questions.
Okay.
If you allow, I don't know your schedule there, so.
I don't know the schedule of the Dirección de Investigación. Denise.
Dígame, profesora.
Podríamos leer una o dos preguntas, no sé si los participantes todavía están allí, para responderles.
Adelante, profesora.
Ok. Déjeme ver aquí si todavía está William. Ok. William Chen ha hecho dos preguntas. William Chen have two questions. One is taking into account the relationship of cost and price. New semiconductors require more and more new materials. Does obtaining these materials influence production cost?
Oh, production cost. Yeah, when we your question is when we consider the production cost, how we can consider the future direction. So that is the question.
If these new materials, to develop this new material, the new materials imply that the production cost will rise or reduce.
For production cost, yeah. So for when we consider the wide band gap material, so production cost is reducing. So at present, wafer cost is very high. A gallium nitride wafer, silicon carbide, so very expensive wafer. But the mass production is going on, so the wafer production cost is reducing. And for gallium nitride and aluminum nitride, so the wafer production technology is now improving, and mass production cost is reducing. But when we consider the device processing, so very minute structure, so nanostructures, in this case, the production cost will be going up. So in some region area, so the price is going down, but in some field, price is going up. And finally, how much is the price? I don't know. Yeah, but basically, probably high performance devices, I guess that the final price will going up. So, but the material so price will be going down.
Okay. Jose Simmons asks, what would you recommend as a roadmap or pathway for the research of quantum dots for single photon emission for the development of technologies focused on the area of healthcare?
Healthcare, okay. For healthcare, so quantum technologies will be utilized for a detection system. So now quantum dot nanoparticles are already under application to detect the some chemical molecules. So that is related to the cancer and other source of diseases. And for a very small size device will be fabricated to detect that kind of diseases. So, but for quantum dots, so many people are studying about the function of quantum dots for various fields, including healthcare. And for optical communication, quantum dot is a source of single photon. But so there's a very severe problem. The emission rate is very low, indicating the information transport rate is low. So we cannot increase the size of the information. So that is a very severe problem, even though the security is going up. So some other method of quantum communication is researched. So for example, the spectral diffusing. So the very low intensity and so covering the wide wavelength region. So that is one method. So, but probably I guess that many other technologies will be developed. I believe. Of course, I'm now considering one method for the quantum communication with high communication rate.
Very interesting. Okay, thank you very much, Dr. Ishitani. Very good. Very, very good presentation. Thank you so much. We appreciate your time, knowledge.
It's my pleasure.
Everything. Thank you so much.
Thank you, Dr. Ishitani, also, and I hope that this is the beginning of a new stage in the academic collaboration between Chiba University and Panama Technological University. Yeah. We are trying to expand the areas of cooperation between Panama and Japan, and Chiba University plays a central role in this effort. It was the first university to establish an academic agreement with a Panamanian university and Japanese university. So we are very happy that you could devote your time today to give us some insights from semiconductors or from your experience and connecting your department now with Panama Technological University. Thank you very much.
Thank you.
Many claps and many.
Buenas noches.
Thank you. It's my pleasure.
Bueno, Eli Denis, ahora sí podemos ya.
Thank you, Professor Ishitani, for your time.